All right, welcome. Today we're going to do substitution. It's a very powerful technique for doing many integrals, and, well, it's really kind of fun. All right, let's start with an example. We'll justify why this example works a little more formally later, but it seems very intuitive. So let's consider this example. Say we wanted to find an antiderivative for 2x sine of x squared dx. Now that's not immediately on the list of the functions that we know the derivatives of, but with some practice you would recognize, oh, this was a chain rule problem that someone took the derivative of sine of x squared. Okay? All right, sometimes that's not as easy to see as it is maybe in this case, but anyway, substitution is a method to kind of work through that and help you discover what's going on without having to think too hard. What we're going to do is kind of notice in our head that this part is sort of the inside complicated part of what we're trying to integrate. Okay? And in an ideal world, it'll be inside something. Not always, but ideally, in the easy cases, it'll be the inside complicated part. And whenever we see the derivative of the inside complicated part, 2x, or up to a constant multiple, it's always a scenario where we know we'll win with this technique. All right? But anyway, the trick is this. When you see a setup that looks kind of like this, you can make a substitution, and you let u be the function x squared. This is the substitution. Okay? And then you take the derivative, du dx, you get 2x, and this is the part that's called the differential. Okay? You move the dx to the other side, you get du equals 2x dx, all right? And then you observe the following. In this integral, we wanted to integrate the 2x sine of x squared dx. This 2x and the dx, when they're multiplied together, that's just over here, 2x dx. That's just a du. And this x squared was just what we called u. Okay? So, if you collapse all this, this is just the same as integrating u du. Now, u du is trivial. It's 1/2 u squared. Oops. This should have been sine of u du. Sorry about that. This is still easy to do. So the antiderivative of sine will be a minus cosine of u plus c. Now remember, u was a new variable that we introduced way up here, and it was just x squared. So to finish the problem, you put it back in. So it'll be minus cosine of x squared plus c. And there you've done the integral in a very sort of mindless way. Okay? All right, let's try another example. Let's do the integral of x squared plus 9, all to the 5th power dx. Okay? So we say to ourselves, this part here looks sort of like the inside complicated part, so I'm going to let u be x squared plus 9. I see the derivative, at least up to a constant of that, because the derivative is 2x, so that gives me strong confidence that the problem is going to work. So it'll probably work out just fine whenever this scenario happens. All right, so let's try it. So the integral of x squared plus 9 to the 5th dx. I'm going to come over here and let u equals x squared plus 9, so that du dx is 2x. And that lets me solve for the du as 2x dx. Now, I just see x dx over here, not the 2, so I'm going to move it to the other side. 1/2 of du is x dx. All right, so this integral here, this part here, the x dx by this part over here is just 1/2 of a du. This part here is just going to be a u. Okay, x squared plus 9 was what u was. So altogether we get 1/2 du and then u to the 5th. People pull the scalar out usually right away. U to the 5th du, or the constant they pull out right away. And then this is easy to integrate, so it's 1/2. Had to come from u to the 6th, so I need an extra 6. And then don't forget that u was x squared plus 9, so this is 1/12 x squared plus 9 plus our constant. Okay? And that's it. That's how substitution works. See ya.